Okay, so today we'll look at the topic which is processing of discrete time signals using continuous time system. So what are we doing here is we have a continuous time system given to us. We have a continuous time system given to us, and we are trying to process a discrete time signal. We have a discrete time signal with us, and we expect the processed output to be also discrete time, but we need to do that using a continuous time system. So obviously we'll have to, at the front end, we'll have to have some kind of a system which is converting this discrete time system signal to continuous time signal. Okay, it's a D2C converter, and whatever is processed by this continuous time system will have to be converted back to discrete time. Okay, because your output will be a continuous time signal, and you give back the y of n. So assuming that this is x of n and these intermediate signals are xc of t and yc of t, okay, we'll have a look at it, like what will be the frequency response of such a system. Okay, so we are looking at it like assuming that this continuous time system, right, the continuous time system given to us has got an impulse response of hc of t, and it's got a frequency response of hc of j omega. This is there given. Okay, now what we are trying to find out is what will be the impulse response of such a system, because you know that this system behaves like a discrete time system. This system, to a person who is looking at it as like a black box, this is a black box to that guy, and this acts like a discrete time system. Although there is a internally they have a converters, but this acts like a discrete time system, and we want to find out what will be the effective e raised to j omega for such a system. Okay, so this is what we are trying to find out here. So first thing we know is how is x continuous of j omega related to x of e raised to j omega. You know that this guy here has got a frequency response of x of e raised to j omega. This guy here has got a frequency response of x continuous of j omega. We know that D2C converter has got a conversion which is happening. X of n gets converted to a impulse train first, and then this impulse train is passed through a reconstruction filter having let's say a impulse response of hr of j omega and frequency response of hr of j omega and impulse response of hr of t to give you the x continuous of t. So how is x continuous of j omega related to x of n? This will be x continuous of j omega will be equal to xs of j omega into hr of j omega. This is your first relation. So xs of j omega is equal to x of e raised to j omega t. It's same as your x of e raised to j omega, but at omega equal to omega t you will get x of e raised to j omega. Okay, so this is your second equation. Now x continuous of j omega will be equal to x of e raised to j omega t into hr of j omega. You know that hr of j omega has got a value of t from minus pi by t less than equal to omega less than equal to pi by t. It only exists from minus pi by 2 to pi by t, and it is 0 otherwise. This is also known. So what we can do is we can say that x continuous of j omega is equal to t into h of e raised to j omega t from minus pi by t less than equal to omega less than equal to pi by t, and it is 0 otherwise. Okay, otherwise So now this xc of j omega, when it is passed through a discrete time, a continuous time system here. So this is xc of here. You want to find out yc of j omega here. Okay. So you know that yc. So your input is, this is xc of t passed through a continuous time system having hc of t and hc of j omega. These are your responses, okay, of that continuous time system, and you get yc of t. So what you have is yc of j omega will be equal to x continuous of j omega into hc of j omega. This is also known. So you know that xc of j omega exists only for, sorry, this is one thing I got it wrong. So this is h. Okay, so this is, yeah, let me just, this is where this will be x. Okay, so you know that this is t into x of e raised to j omega t into e raised to j omega t into h continuous of j omega from minus pi by t less than equal to omega less than equal to pi by t, and it is 0 otherwise. This is what you will have, right? So this is just one correction here. X continuous of j omega is t into x of e raised to j omega t, and then I substitute it here. I get this y continuous of j omega. This is my fourth one relation. This is fourth relation. Okay, so this was the third one. This is the fourth one. Okay, so now this yc of t is passed through a C2D converter. Now yc of t is passed through a C2D converter. This we already know what happens here is when you pass a xc of t, or sorry, yc of t through this C2D converter, you get your y of n. And how is this y of n related? This has got a frequency response of y of e raised to j omega. This has got a frequency response of j omega, yc of j omega. So now let me just add a page. So now here what will happen is, I know that y of e raised to j omega is 1 upon t, because your C2D converter here has got what? It's got a multiplier. Okay, x yc of t into p of t, and this is passed through a from train to impulse train to discrete time sequence, and you get your y of n. This is your ys of t. We know that. One more thing to note is we have to supply this with the periods, right? So this is t, assuming that this is t and this is also t. Okay, so this is the sampling, this is the cutoff for a reconstruction filter. This is the sampling rate. Okay, so now once this is known, so you know that this y of e raised to j omega is summation k equal to minus infinity to infinity y continuous of j omega by t minus 2 pi k by t. This is also, we have done this lot of times. So I am interested in yc of j omega only for one period now, only for one period. So yc of j omega t, whatever it is, let's say this is your yc of j omega. These are multiple copies that you have. Okay, these are multiple copies that you have. I am interested in only one copy right now, which is centered around 0. This is centered around 2 pi by t, this is centered around minus 2 pi by t, and so on. But I am only interested in is not when k equal to 0. So what I'll get here is 1 upon t yc of, so have yc of j omega by t, which is your spectrum around 0. Okay, now this yc of j omega t, which is related to the this particular here expression is the spectrum around 0, right? Because you know that this HR of j omega is from minus pi by t to pi by t. So this will turn out to be equal to 1 by t into t. By substituting this particular expression here into this, what we get is x of e raised to j omega by t into t, just substituting omega equal to omega by t here, right? So what you get here is into hc of j omega by t. Okay, so this turns out y of e raised to j omega is equal to x of e raised to j omega into hc of j omega by t. This is what you get. Now if you look at this expression carefully, what is this is my effective h effective of e raised to j omega. This is what you have. So h effective of e raised to j omega is equal to hc of j omega by t for minus pi less than equal to omega less than equal to pi. So, okay.